Hello everybody, welcome back to our channel. In today's video, we're going to be working on this PHY7B momentum practice problem, the rocket's mission. As usual, if you're enjoying these videos and you found them useful, please make sure to leave a like and subscribe. It really helps this channel a lot. So the problem statement goes as follows, and feel free to pause the video to copy the problem yourself. So we have a rocket that's on a mission to divert an asteroid. The asteroid is moving towards the Earth, and it must be diverted by 2 times 10 to the negative 6 degrees from its current path in order to safely miss the Earth. The question here is, if the rocket's thrusters can output a force of 4 times 10 to the 5 newtons perpendicular to the asteroid's path, how long must the thrusters be on? And then they give us a hint, how big does delta P need to be? So as you can see, I've copied all of the relevant information in my notes. So we do have a mass of the asteroid, an initial velocity. We know that it must be diverted by 2 times 10 to the negative 6 degrees, and this is the force that the rocket can put on the asteroid. So you can see the scenario in this little drawing that I made. So if the asteroid were to follow this path, which is the path that it is going to hit the Earth. However, a scientist, basically figure out that if we can modify this by as little as 2 times 10 to the negative 6 degrees, then the asteroid is gonna follow this path instead, and it's gonna miss the Earth. So that is basically what we want. So let's just get started by trying to figure out a momentum chart. As you can see, I have a little momentum chart over here. They are a very helpful visual tool. I'm always gonna do a momentum chart if I can. So let's just get started. The first thing that I'm going to do is fill in the information that I have. So I do have an initial mass, and I do have a mass, and I have an initial velocity. So I'm just going to go ahead and multiply those numbers in order to get an initial momentum. So let's just go ahead and do that. So that is mass asteroid B initial asteroid. So this is 10 to the 12 times. Please notice that the problem gave us the velocity of the asteroids in kilometers per second, and I decided to convert that into meters per second just because otherwise I would totally forget about it, and we do need SI units. So this number is just going to be 35 times 12, 13, 14, 15. So 35 times 10 to the 15. There we go. So now the next thing that we have to do, oh no, it's 10 to the 12, so that would be 16. Sorry about that. And according to my drawing, I just decided that everything was going to be on the X trajectory at the beginning. If your drawing looks a little bit different, then just make sure that your momentum chart looks is in agreement with that. At the end, the math is going to be the same, so it doesn't matter, but there are several ways in which you can actually draw this problem. So now what we want over here is a diverted asteroid. So we don't really have a magnitude at the moment. The only thing that we know is that this diverted asteroid is going to have an angle right here of 2 times 10 to the negative 6 degrees. So we have an angle. We don't really have a magnitude, and that is what's really, that's what really sets this problem apart. Now, in terms of delta P, I can't actually figure that out just yet because I don't really have a magnitude here. However, I do know that because the initial momentum plus delta P has to be equal to the final momentum, that delta P is basically something that looks like this. Because if you think about it, this PI is basically this component over here. So this needs to be delta P in order to have this P final. And that is basically what's going to give you this trajectory with this angle right here. So now, how do we figure out the value of delta P? Because that's really what that is in reality what we want to get out of this problem. Well, we can basically use SOHCAHTOA, right? Yeah, I think so. We need to use SOHCAHTOA. So let me just go ahead and draw this exact triangle. So let me just draw it over here, I guess. Now I have this angle. So how can I figure out this thing over here? Is there a way for me to figure it out? Yes, there is. I can actually use tangent, because if you just look at your SOHCAHTOA, tangent of this angle is equal to delta P divided by P initial, and I do have P initial and I do have this angle, so delta P is just gonna be Pi tangent of my angle. So delta P is just gonna be, so let's see, let's just multiply those numbers. So it's 10 to the 12. So we have 10 to the 12. Let's just put this in parentheses here. And then we have tangent of 2 times 10 to the -6. And that is going to give us just this big number that I'm going to copy. So it's 34906.58, and then the units is of course kilograms meters per second, but that is not as important right now. Okay, so we do have a delta P value, and that is actually gonna be very useful in order to solve this problem, because now that we have this delta P, we can just go ahead and use our main momentum equation, the one that goes delta P is equal to F net delta T. Delta P we already figured out, so this delta P is just this number. The net force in this case is equal to the force by rocket, because we are in space, so there aren't really any other forces. So because we only have one force, the force by rocket is going to be the net force for this scenario, and delta T is basically what we want to figure out. So delta T is going to be equal to delta P divided by F by rocket. So I'm just going to go ahead and divide this big number by 4 times 10 to the 5. Okay guys, I'm sorry, it seems that my calculator was not in radians, so this number is actually not correct. I recalculated the number and I have a different number, so I'm just gonna go ahead and put that down. So it's 1.22 times 10 to the 10 right here. Okay, so that is actually gonna make this make sense. So just going back to what I was working with, everything else is exactly the same. It was just a little bit of a calculator issue, but now I'm just gonna go ahead and divide this delta P divided by force by rocket, which is just this number that I got as an answer divided by 4 times 10 to the 5, and there we go. So that is 30543.2 seconds. So if we divide it by 60, that is somewhere around 50 minutes. Yeah, there we go. But here's our answer in seconds. Here's how you get the 30,000 seconds essentially. I just had a little bit of an issue with my calculator. I was working on another different problem and I just changed it. But now that I changed it back into degrees, this is the actual number and this is the actual final answer for a problem. Everything else is correct. It was just a small issue. So anyways, I really hope that this was useful for you. Again, if you are liking these problems, you're finding them useful, a like and subscribe is very much appreciated. I'll see you guys in the next video. Bye bye.